Hello and welcome back to computer organization class. So we have been discussing about assembly language. We have looked at different aspects of assembly language. Namely, we looked at different machine models and how those machine models basically define how many explicitly mentioned operands should be there in the assembly instructions. Then we looked at the different addressing modes and how those addressing modes actually define the characteristics of the assembly program. And in the last class we started looking into different arithmetic and logic operations or instructions. We looked at some interesting instructions like or operations like shift operation, and we also briefly looked at how using shift operation you can do really do multiplication, division kind of operations in much simpler way, so that saves lot of your hardware resources as well as time. So that is very important. So if you can convert a multiplication or division operation as a shift operation, that is that saves lot of your time. Now we will continue our discussion from there, and today we will look into we will start looking into load store operations, and followed by that we will be looking into other instructions, and then how different branch instruction, the functions, how functions can be written, how functions actually get implemented. So those things we will be discussing in today's lecture. All right, so let me start okay. So we will start our discussion with load store instructions. So in different stages in our discussion, we have already seen what these load store instructions are capable of, or what are the purpose, but we will look into them in more closely, how actually load store happens in an hardware. All right. So now typically the load store instruction in assembly, and for the simple RISC example which we will be sticking to, but this is true for mostly most of the simple RISC assembly instructions. So if you understand this, you should be able to understand other instruction as well. So basically load instruction will have a destination. So this is your destination R1, let's say, followed by the address from where you have to get the data to load in R1. So the data generally will be represented or the address will be generally represented in the base offset addressing mode. So we have looked at different addressing modes. So let's assume that in this case the address will be denoted as base basically base offset addressing mode. So our base address is stored in the register R2 and the offset value is 10, and this is the location from where you will get the value to be loaded in R1. So this load instruction will imply that R1 will be moved or the content of this location R2 plus 10 will be moved into the register R1. Okay. So why this base address addressing mode? Because this is a very generic addressing mode, and it can help us we will see in our subsequent discussion that it helps us a lot in pointing to memory in a very systematic manner. Like if we want to access an array, then it becomes much more easier with this base offset addressing mode. So what we are doing here, we are fetching the content of R2 and then adding the offset to it, and after that we basically this is the address from where we have to get the value. We access that memory location and load this data into R1. So this is our destination. All right. Similarly, we can have store. So what does store? What will store do? Store will have basically the content of R1 needs to be stored in a location, and we can do the same kind of basically base offset addressing, where we say that okay, this is the location where the value needs to be stored. So what we will do here, so this is the location R2 plus 10, the memory location where the content of R1 will be stored. Okay. So easy way to remember is that this is your register and this is your memory. All right. So the load will send data from memory to register, and the store will basically store the value of register into memory. I think it's very intuitive. We can also look at it pictorially, which I guess will just recap your memory that we have these registers files. Okay. So let's say this is where your R1 is, and you will add this offset with the content of register, and you will point to the memory. Okay. So let's say this is the location where you point, and depending on, let's say if it is an integer value, so it will need 4 bytes to store the data. So this is the starting of the 4 bytes. So subsequent to this, these are the 4 bytes where your data will be loaded from. So we are looking at load instruction now, let's say. So this is load. So what we will load? So the same instruction which we have seen here, we are trying to see it pictorially. So this is our destination. So the data has to come. So this is my data which I want to load. So it will come back and I will store it here in this R1. Now how I will find where to get the data from? So I will look at the, okay, I need to look at the content of R2. So sorry, this will be R2. So I read R2, I add this offset 10, and that will point towards to the first byte of the 4 bytes which I need to bring in to store it in R1. All right. Hope this makes sense. So similarly, in case of store, you will be doing the other way around. So basically, you will be reading the value of. So in case of store, you have your register files. So this is your R1, R2. So in R1, you will be storing the data. Basically, the data of R1 will be stored in this location. So basically the data goes to this memory. Now where the data will go, that will be determined by this register and the offset value. All right. So offset of 10 will be added. This is your register file. So you read the value of R2, add the offset, that denote the location where you need to store the value of R1, store the content of R1. So basically this is how you will perform the load operation. All right. So I hope this this is pretty clear. Now just to hammer this point more strongly, let's look at an example. So example of an array. So we are looking at an example. So let's say I have an array. Let's look at a high level description of an array. So let's say I have an integer array named ARR, and it has 10 elements in it. Okay. So what does this mean? Now I have an integer array and it has 10 elements. So that means for each integer I need 4 bytes. So to store this array I need 4 multiplied by 10, 40 bytes. So let's say I have an array of 40 bytes to store this array. So I have a memory of 40 bytes to store this array. Now let's say subsequent to this there are more instructions or more information about what are the contents of this array. So let's say the third element in this array is 5, then the subsequently let's say fourth element is 8, and the fifth element we would like to store with the addition of basically fourth element and the third element. All right. Now how this will look like in assembly? If I want to translate this into assembly, so how should I look at it, or how this assembly code will look like? Now think about it. We need to basically point towards these elements in this array in assembly. So let's say we store the base of this array. Base of this array is stored in a register R0. So what we are saying? We are saying that the starting point of this array, which contains 10 elements, 10 integers, is stored in register R0. Assume that the base of array is saved in R0. Now this is R0, so the first element of the array can be denoted or can be addressed by R0 plus 0. So here the offset value is 0. Now what will be the second element of the array? The second element will be, so basically this is 1, 2, 3 and 4. So basically let's say 0, 1, 2, 3. So this is the location where the second array will start. So what will be the address? That will be R0 plus 4. Similarly, what will be the address of the third element? It will be R0 plus 8 and so on. So you see that because of this offset base offset addressing mode, we can very easily find out where the different elements of the array will be. Okay. So now if we want to as we are planning to translate this high level code into assembly, the instructions or the assembly code will look like, let's say we move, first we have to move these values to some register. So let's say move R1 with 5. Okay, now 5 needs to be stored into the third element of the array. So this is a stored instruction. So we will be storing the value of R1 store value of R1. Now where should we store? In the third element of this array. So now how the third element will be denoted? So this is the first, second, so this is the basically this is the 0th element, this is the first element, this is the second element, and the third element will be basically R0 plus 12. Does this make sense? So the next is basically we move let's say R2 to basically move 8 into R2, and then we again have this store instruction, store R2, the content of R2. Now where it should be stored? In the fourth element in the array. So fourth element is denoted by the offset 16, right, 16 R0. Alright. Now we can write this simple add instruction, add R1 and R2 and store it in R3. Alright. Now this R3 needs to be stored in the fifth element of the array. So we can write again store basically R3 where? In this location. So basically the offset will be 20 because it's the fifth element, and yeah, the base address remains the same. So I hope this makes sense, and we can deal with load store kind of instructions going forward. Okay. So now another very important instruction, or basically yeah, a very important set of instruction is branch instruction. So as the name suggests, branch instruction basically changes the flow of your code. So generally you fetch instructions from the next location and so on, but branch basically tells you that you are not supposed to fetch the instruction from the immediate in this specific sequence. You have to branch to a different location. So now branch can be of different types. The most simplest of them is unconditional branch. So unconditional branch basically can be denoted very simply like the letter B, and then it will be followed by a level. So the level is nothing but different segments of the code which are denoted by this level. So for example, if I write something like, let's say b dot foo, so foo is the level here. So this means that you branch to the level dot foo. All right. So one simple example can be, let's say you write assembly code like this, add R2 and R3 and store it in R1, then branch to dot foo. So whenever this instruction is done, you decode this instruction, you know that your program counter needs to be updated with this level. So let's say there are several instructions which you will ignore, and then there is a level dot foo where you have this instruction add R3, R1, R4. So basically whenever you see this branch instruction, you branch to here and you execute the subsequent instruction. So this is unconditional branch. So you are not checking any condition or anything. Whenever you encounter this branch instruction, you just branch, or you just jump to that new location. There are more interesting branch instructions which are called conditional branch instructions. So conditional branch instructions, as the name suggests, so it checks some conditions, and depending on the outcome of the condition, the branch is either taken or not taken. So the two conditional branch instruction that we will be we will be dealing with in this here is basically branch if equal. So it's denoted as BEQ. So if the, you remember the compare instruction used to set or reset few flags. So the flags dot equal, then flags dot greater than, these flags were set by compare instruction. Now if those flags are depending on the condition of those flags, this branch instruction will be either taken or not taken. So if the equal flag is set, then this branch instruction will be taken. So branch if equal to dot this level, so this denotes that branch to this level foo if flags dot equal is 1. There can be another conditional branch instruction which is branch greater than. So if the greater than flag is set, then you need to again branch to this level. So these levels are not important, you can define any level. Branch to this level if flags dot gt is set. All right. Now just to remind you that these flags are set only by the compare instruction. So compare instruction so as I said, like BEQ is branch if equal. I hope I don't have to write it down, you will remember that. So if the flags dot e is 1, then jump to this location. If the flags dot gt is 1, then you jump to this location when you are basically writing this BGT instruction. All right. So we can look at a very simple code, example code. So let's say we want to write a code which says that if R1 is greater than R2, then you save 4 in R3, in R3, else you save 5 in R3. So, what we are saying that you check this condition, if R2 is greater than R1 is greater than R2, then you have to update R3 with 4, all right, else you should you should update R3 with 5. So, if I want to write down the assembly code for this, so what I will do, I will first compare this to two registers. So, I will be writing compare R1 R2. Then the next thing I will be doing is I have to check the status of the greater than flag. So, basically I can branch if greater than to, let us say, this level. So, I just name this level as go to level. Now, if this condition is not true, if greater than flag is not set, that means what? That means R2 is greater. So, in that case this condition has to be, or this update needs to be done. So, R3 should be updated with 5. So, move R3 with 5, and then you can end the program or whatever you are supposed to do, you can do. If this condition is true, then you should go to some other location which is denoted by this go to level, right. And what you should do here, you should update R3 with 4. So, move R3 with 4, all right. So, pretty straightforward, nothing very complicated. So, I hope you guys can relate to what we are talking about. So, this is a very important instruction which is basically the branch instruction, all right. Now, with these kind of instructions, we can now start looking into reasonably complex arithmetic operations and arithmetic, let us say, arithmetic manipulations, and we can write assembly code for the same. So, one such example can be figuring out, let us say, factorial. So, if we want to compute the factorial of a variable number, let us say any variable n. So, compute the factorial of the variable, let us say num. Now, whenever you are given this kind of task that you need to write the assembly code for writing such a for performing this operation, it's since we are very used to high level language, so it's best the best approach will be you write the basically high level language code for the same first, and then you translate it to a assembly code. So, if we want to write figure out the or compute the factorial of a number, then in high level language, let us say in C, the code will look something like this. So, we will first initialize our a variable called product with 1, and then we will also have integer named index, denoted as idx. Now, what we should do, we should initialize, basically we will take input this variable num, and then we will initialize index with num, and if the index is greater than 1, then we will keep looping, and inside the loop we will basically multiply or update the product as product multiplied by index. So, I will just write it down, I guess that will be much more clearer. So, for IDX, so IDX will start with num. Now, we will check this condition whether IDX is greater than 1. If so, then we have to basically decrement IDX, and then we will do this updation of product. Product is product multiplied by IDX, and that is it. So, finally, in this variable product we will get the factorial value of num. So, let us say take some example, num is 4. So, we will start with 4. Is 4 greater than 1? Yes. So, product is currently 1, 1 multiplied by 4, you get 4, and since we need to continue this, so now we will update. If I want to write down the assembly code for the same, so how can we write the assembly code? So, we have to basically first initialize, let us say, a variable or a register R1 with 1. So, here we are initializing or we are doing the equivalent of this. We are initializing the variable product with 1. So, we moved the value 1 in R1, then we move R2 with R0. So, basically here we are initializing our index. So, here the assumption is the number we would like to find the factorial of is stored in R0. Alright. Now, we will write down a basically level loop, and then we will do this multiplication of. So, what we are doing, we are simply doing this operation, product is product multiplied by IDX. Alright. So, basically this R1 is getting updated by the product of R1 into R2, and then you subtract basically this index. So, R2 you update with R2 minus 1. So, index is IDX is IDX minus 1. Now, you need to compare CMP, and what all you will compare? You will compare the index R2 with 1. If this is greater, R2 is greater than 1, then you have to perform this loop again. So, basically compare alright. Now, if greater than, so branch if greater than to loop. Alright. So it means that if idx is greater than 1, then you go to dot loop. All right. So I hope this makes sense. Now, very briefly, we would like to talk about something called modifiers. These modifiers are added in the instruction so that we can basically wherever there is an immediate operand. So, because immediate operands will not have, we will not be able to express all the 32 bits in the immediate. So, these modifiers actually play a very important role, and we can since all our arithmetic operations will be 32 bit. So, we have to somehow tell the processor that whatever immediate value we are giving, how to convert it to a 32 bit number, because all the operations will be all the arithmetic operations will be 32 bit, right. So, this is where the modifiers help us. So, by default, if by default the modifiers so I'll just give you the definitions first, and then we will maybe understand. So if it is default, so remember modifiers are there for instruction where there is a immediate operand. For instructions that has an immediate operand. Alright. So, the default modifier, if there is this is default, then let us say we write an instructions like move some immediate value to some register. So, in that case the immediate value will be, let us say, 16 bit immediate value. Now, in that case what we will do, we will treat the 16 bit immediate as a signed number. Alright. So, the 16 bit immediate will be treated as a signed number. So, if it is a signed number, so this 16 bit immediate number will be converted to a 32 bit number by sign extension. So, basically automatic sign extension. If it is a positive number, the basically MSBs will be filled with zeros. If it is a negative number, then all the two most significant bytes will be basically ones. So, automatic sign extension. Alright. Now, I can have a modifier which is denoted as U. So, U modifier. So, how this will be used? So, basically you will see that move U. So, with the move instruction there is a U attached to it. So, if this modifier is added, that means you have to treat the 16 bit immediate as an unsigned number. U stands for unsigned. all right. So, basically the 16-bit number will be considered as unsigned number. So, the upper or the MS most significant 2 bytes will be zeros. There is another modifier which is called H modifier. So, this will make this move instructions like this. So, it says that left shift the 16-bit immediate by 16 position. So, what it says, left shift the 16-bit immediate by 16 position. All right. So, we will look into it through an example. So, why we need these modifiers? Because the processor internally converts a 16-bit immediate to a 32-bit number. Because it uses this 32-bit number for all its computations, and this kind of immediate this kind of modifiers are only valid for arithmetic operations. Now, we can control the generation of these 32-bit numbers using these modifiers. For example, if we say that okay, there is we do not want anything, so automatically by default it will be the sign bits, sign extension. If we add this u suffix, that means the 16-bit number will be basically treated as an unsigned number, and if we have this h suffix, then this 16-bit number will be the basically the more significant 2 bytes of our 32-bit number. So, I will try to show it pictorially. So, let us say we try to understand these modifiers, and we look at these different cases. So, let us say I have an instruction like this: move R1 with this immediate value. So, the immediate value is A, B, 1, 2, right. Now, this is a 16-bit number, our immediate is a 16-bit number. Now, this is my R1, it is a 32-bit register, all right. So, basically this is my 32-bit register. So, if it is nothing is no modifier is attached or no modifier is mentioned, that means it is the by default situation. So, what I will do, I will put AB here, 1 to here, and these will be my sign bits. So, I will just extend my sign bits, right. Similarly, I can have an instruction like this, move U R1, let us say the same number, that is AB1. So, what will be the case here? So, this is unsigned. So, in case of unsigned, AB and 1, 2 will be occupying this, and for unsigned these are simply zeros. Another example is move H, and let us say we stick to the same example, all right. So, here the R1, the more significant bytes will be populated by this value, and the lower significant bits will be populated with 0, all right. Similarly, we can think of let's say if an example, if we want to store or let's say we want to initialize R0, the register R0 with this value. So, we will not be able to write a single instruction because let's say I want to initialize my R0 with this 32 bit immediate. Now, we can't have 32 bit immediate directly, but we can use these modifiers to do that. So, how? So, we can use move h to populate the higher 2 bytes with these two values. So, basically R0 with 12 AB, alright. So, now R0, the more significant 2 bytes are populated by 12 and AB. Now, how can I add this part of into R0? So, I can just go ahead with the unsigned move, or okay, not move, let us say we can just do add, unsigned add, and if we add R0, so R0 current content is this because the lower bytes are 00. So, if I add 0xA9 to D, then ultimately I will have this R0 initialized by this 32 bit immediate value, alright. So, in this way, in an indirect manner, we can initialize our registers with 32 bit values. Okay. So, this we have so far looked into most of the logical and arithmetic and let us say memory related like load, store operations, branch instructions, and we have also looked at the modifiers modifiers to see how immediate values can be used. Now, going forward, what we will do, we will look into few more things which are essential to really write complicated or non-trivial programs, and those concepts are basically like functions, how functions can be written in assembly, and then how actually these functions are, how you pass your arguments in these functions, whether your the general purpose registers will be sufficient to pass all the arguments. If not, then what are the way outs. So, that is what we will be discussing in our subsequent lecture. All right.